Welcome to our lesson on overseeing modifications and providing governance for artificial intelligence systems. Today we will explore why updating machine learning applications requires an entirely different approach compared to traditional software maintenance. We will examine the critical nature of information inputs, adjustments to the core predictive engines, the influence of evolving laws and public opinion, and the unique strategies required for urgent system repairs. Understanding this framework is incredibly valuable for your daily professional life. When your company needs to alter an automated decision tool or respond to a sudden malfunction, you will know exactly how to evaluate the safety of the proposed fixes and ensure the system remains compliant. This enables you to confidently guide engineering teams away from outdated patching methods and towards safe, modern governance practices. Let us start by looking at a concept known as data dependency. Traditional software operates strictly on rigid instructions written by a programmer. Artificial intelligence is fundamentally different because it relies completely on the information it ingests to function. Because of this reliance, these systems are highly vulnerable to any shifts in the underlying information used to teach them, as well as where that information comes from. When an application is initially built, it expects the incoming information to meet very strict standards for format, quality, and relevance. If the characteristics of the incoming information suddenly shift, the system might produce errors or fail entirely. To handle raw information, organizations use a method called preprocessing. Preprocessing simply means cleaning and standardizing raw inputs so the computer can easily digest them. If the source information changes, the preprocessing steps must also be updated to keep the system running properly. Think of a high-end juicer designed specifically to handle peeled oranges. If your fruit supplier suddenly starts sending pineapples, the juicer will jam. You would need to add a new preparation step to core and slice the pineapples before they go into the machine. Additionally, information changes naturally over time in a process called data drift. Data drift happens when real-world conditions naturally evolve, such as shifting consumer buying habits, seasonal weather changes, or the emergence of entirely new categories of goods. Because the real world never stops changing, any strong governance program must actively monitor for data drift to ensure the application remains accurate. Next, we must discuss the management of the predictive engine itself, commonly referred to as the model. The model is the central brain that identifies patterns and generates outputs. During operation, users can often tweak how this brain behaves by adjusting specific settings known as inference parameters. An inference parameter is simply a dial that controls a specific trait of the output, such as how strictly the system sticks to facts versus how much randomness it introduces. Changing just one of these dials can drastically alter the creativity and variability of the results. Beyond tweaking settings, companies frequently upgrade their systems by completely swapping out an old predictive engine for a newer version. When an engine is swapped, the entire behavior of the application can change overnight. This introduces a challenge known as opaqueness. Opaqueness refers to the inability of humans to clearly see or understand the internal logic the system uses to reach its conclusions. Different predictive engines have varying levels of opaqueness depending on how they were built and the ethical standards of their creators. Imagine hiring a new master chef for your restaurant who refuses to share their secret recipes. You know the food tastes different, but the exact cooking process is completely hidden from you. Because of this hidden complexity, any modifications to the core engines must be strictly controlled by corporate oversight policies. We also need to evaluate the broader external environment, specifically the legal and social impacts of this technology. As these tools become more common, they face intense public scrutiny. Lawmakers are constantly working to establish new legal boundaries and safety requirements, meaning the compliance landscape is always moving. At the same time, public opinion is mixed. A major social concern is the fear that automated tools will permanently replace human jobs. Whenever an organization introduces a major technological shift, they must perform a workforce impact analysis. This analysis involves studying how the new tool will disrupt daily tasks and figuring out how to retrain staff for new roles. Consider the transition from horse-drawn carriages to motorized taxis. The shift eliminated the need for carriage drivers but created massive new industries for mechanics and factory line workers. Companies must monitor evolving laws and actively support their employees through these transitions, offering the time and training needed to adapt. Now let us look at the critical procedure for handling urgent malfunctions. With standard software, a developer can usually write and deploy a quick line of code to fix a bug in a matter of hours. Machine learning tools do not allow for this. Rebuilding and teaching a system from scratch to remove a flaw can take weeks, which is far too slow during a crisis. Instead, organizations must use alternative strategies. The first strategy is a rollback. A rollback means intentionally reverting the application to an older, previously saved version, provided the older version does not share the same defect. The second strategy is applying input and output validation. This involves placing independent, standard software checkpoints both in front of and behind the predictive engine. These checkpoints act as shields, filtering out toxic requests before they enter and blocking dangerous answers before they reach the user. Think of a municipal water supply that suddenly gets contaminated at the main processing plant. You cannot rebuild the entire plant in one day. Instead, you either switch back to using the old reservoir, which is our rollback, or you distribute external water filters to every home to catch the impurities at the tap, which is our validation method. Crucially, any urgent intervention must be reviewed and authorized by key stakeholders, following the exact same rigorous approval channels used for standard IT emergencies. Another fundamental requirement is configuration management. This is the practice of meticulously recording and locking in the precise settings of a system. For automated tools, maintaining absolute uniformity between the testing lab and the live public environment is mandatory. The exact same data cleaning steps used during development must be used when the tool goes live. Furthermore, the system relies on a technique called tokenization. Tokenization is the process of chopping up raw text or images into tiny numerical fragments that the computer can actually read. If the method used to chop up this data differs between the lab and the real world, the system will completely fail to understand the user. Finally, we must address the ultimate supervision of these technologies. Decades of advancement have led to tools that operate with very high autonomy, meaning they can make complex choices entirely on their own in unpredictable situations. Because they operate so independently, companies must implement continuous, robust oversight programs to intervene if the tool creates safety hazards or ethical violations. If you hire a highly capable general manager to run a store autonomously, you still need to conduct periodic audits to ensure they are treating customers fairly and following safety protocols. Let us quickly summarize our main points. We established that automated tools are highly dependent on information, making them susceptible to real-world data drift and requiring identical cleaning steps in both testing and live environments. We learned that adjusting settings or replacing engines completely alters behavior, which requires strict governance due to the hidden nature of their internal logic. We discussed the importance of monitoring legal trends and supporting staff through workforce transitions. We explored how urgent repairs require unique tactics like version rollbacks and external filtering shields. And lastly, we highlighted that highly independent tools demand ongoing human oversight to prevent ethical failures. All the concepts we just discussed are tested in the multiple choice questions on RooCloud.com. You should ideally solve the chapter-wise questions there to reinforce your learning and ensure you're exam ready before moving on to the next session. Keep up the excellent momentum, and I will see you in the next lesson.